Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be going over and reviewing the equilibrium constant for reactions that are in equilibrium. So let's go over this. Okay, so you may have in your chemistry class gone over reactions, and it may seem that a lot of the reactions you've been going over in class go in only one direction, right? They go 100% towards the products. And so in a lot of those equations you're writing there's only like one arrow, it goes in one direction, and you're completely forming all of the product. That would be only a very small fraction of reactions actually really go 100%, if any, right? So the vast majority of reactions, if any reactions, are in equilibrium, right? So there may not be any reactions that are not in equilibrium, right? There might be a very small handful, but the vast majority are in some sort of equilibrium. We call that dynamic equilibrium that I'll be talking about in this video. So for reactions that are in equilibrium, for some reactions it seems like they go all the way 100%, but in reality, there's just a little bit of reactants left, and there's a dynamic equilibrium there. And what I mean by dynamic equilibrium is that as you are forming product, the products can also then form reactants. So there's a back and forth going on there. And so in this case, when we talk about dynamic equilibrium, we're talking about the rate at which products are formed compared to the rate at which the reactants are reformed from the products. So here's an example. Here's your a generic equation at equilibrium. You'll notice the double arrow here. So here, the way to understand this is that the small letters represent coefficients in your equation. The large letters represent the substances themselves, the species, reactants, and products. And so here you see that the reactants A and B can form products C and D. So you have that top arrow going this way, so reactants form products. And you can see that you have this bottom arrow going in the reverse direction, and that means that the C and D, once you form these products can then combine and react and reform the reactants A and B. So there's a dynamic equilibrium going on there, right? So what do we mean by dynamic equilibrium again is if we have a certain rate going this way, so there's a rate of the reaction going in the forward direction where the reactants are forming products, there's also a rate at which the products are going to then reform the reactants, and this is happening at the same time. But there's going to be a point at which the rates are equal. So the number of reactants, right, the rate at which the reactants are forming products is going to be the same as the rate of the products reforming reactants, and it's happening at the same time. The analogy that I like for this process is that of immigration from one country to another, right? So if you have two countries bordering each other, or if if you have states, right? I live in the United States, so we have states bordering each other. And so people are kind of traveling back and forth between states. People move from one country to a neighboring country, right? So again, I have Canada. Canada is above us, so we might have people immigrating back and forth between the United States and Canada, or between different states like Illinois and Wisconsin, if you will. Right, so people are moving back and forth between the states, and so there you have fluctuations. So you have people who might be moving in this direction, moving to a different country or neighboring state. But then you have people from the other, the next door neighboring state moving in the opposite direction to their neighboring state, right? So you got this back and forth, and so the dynamic equilibrium is represented there because you have people traveling in both directions, and so if you have a faster rate going this way, then the population of this state or country is going to grow compared to this one, right? So if you have less people traveling this way, more people traveling this way, then this country will grow in a population, and the population is going to change. And then this population is going to decrease, but you're going to reach some sort of equilibrium at a point, right, where the flow of people moving in this direction and the flow of people moving in this direction is going to equalize, okay? So what does that mean? It just means that the rate at which people are moving this way is equal to the rate at which people is moving this way. Now, does that mean that this concentration or the number of people is the same as the number of people on this side? No, it's just the rates at which people are moving, right? And so that's the same thing that's happening with the equilibrium, with a chemical equation. So reactants are forming products at a certain rate, and then products are reforming reactants at a certain rate. When those rates are equal, you now have equilibrium, right? That does not mean that the concentration of these things, the reactants, is equal to the concentration of the products. They're going to be different, and that's what our equilibrium constant will tell us. What will be the concentrations of reactants versus products at equilibrium, okay? And also at equilibrium with my immigration example, right? The analogy. The people on this side are going to be always changing. It doesn't mean you have the same people each time, because again, people are still moving this way to the other country, and people are still moving this way to their neighboring country over in this direction. So over time, the number of people here will stay constant, but if you take a snapshot at one time and you take a snapshot at another time, you'll notice that even though the number of people is the same, who makes up those people are going to be different, right? Because there's constant fluctuation. And again, it's the same with chemical reactions. So let's go ahead and talk about the KEQ. So the KEQ, or the equilibrium constant, is equals this expression here. So given my generic equation here, you'll see that the equilibrium constant is equal to the concentration of product C raised to the C coefficient. Remember, the little c is the coefficient of C, little d is the coefficient of D. So I take the concentration of C and I raise it to the power of the coefficient of C. And I multiply that by the other product, D, and raise that to the coefficient of its, the power of its coefficient, which is little d, right? And if I have more than two products, then I would multiply by the next product. So if I had E here, then it would be multiplied by E raised to the E coefficient, and so on. So I have the products here, and then they're going to be divided by the reactants. The concentration of the reactant of A raised to the A coefficient, multiplied by the concentration of B raised to the B coefficient, and so on. If I had another reactant, if I had a third reactant, it would be multiplied by the concentration of that reactant raised to its coefficient. So that is the expression, and that's how you calculate the equilibrium constant. And these are, by the way, these are concentrations at equilibrium. Once the equation or the reaction is at equilibrium, then you plug in your equilibrium concentrations raised to the powers of the coefficients of the reaction equation, and you can calculate your equilibrium constant. More generally, the way you can understand this is by the concentration of products over the concentration of reactions. P for products, R for reactants. So that's generally, very, very generally, what the equilibrium constant is. It's a ratio of the concentration of products over the concentration of reactants. So let's go ahead and look at what K means and what K can tell us about the equilibrium of different reactions. So what if KEQ, or the equilibrium constant, what if that is large? Okay, so here we have an example of a reaction here where the KEQ is large. So we have silver aqueous ions, silver ions dissolved in water, reacting with ammonia to form this silver ammonia ion complex, right? So here we have this reaction at equilibrium, and you'll notice here that the equilibrium constant for this reaction is 1.6 times 10 to the 7. So that's a very large KEQ. What does that mean? Well, it just means that if we understand that KEQ is concentration of products over reactants, right? Products over reactants, then that means for KEQ to be very large means that the numerator here is much, much greater than the denominator. So the denominator is small and the numerator is large. And so that means that this reaction favors or likes to form products, right? So at equilibrium for this reaction, I'm going to have a huge amount of product compared to the amount of reactant, right? Because reactants are on the bottom, product is on top, right? So if this KEQ is very large, then that just means that I have a very large numerator compared to the denominator. So the denominator is going to be very small, meaning the reactants, the amount of reactants I have at equilibrium is going to be very small. And the amount of product I have at equilibrium is going to be very large, giving me a KEQ that's very large. So if I was to take a snapshot of what this looks like in the solution, right, at equilibrium, if I just was able to take a microscopic picture, then what I would see all three of these in solution. They would all be there in solution. However, I would have a huge amount of this in solution and very little of this. So from the macroscopic view, it would look like this reaction went 100% this way. It like completely formed this product and I have none of this left. However, at the microscopic level, if I was to take a picture, I would still see some of this, right? And so again, we're in a dynamic equilibrium, so this is still going to be forming product while the product is going to be reforming reactant. So this is still going on. So again, if I take a later snapshot, the silver and ammonium species that I had in solution would not be the exact same silver ions and ammonium molecules that I had before. They would be different, but it would be the same number, right? So because of the equilibrium we're in, the rate going this way is the same as the rate going that way. So that allows for the concentrations of these things to stay the same, but the actual individual ions and molecules that are participating in the reaction, that the ones we find in solution are going to be different ones, okay? So that would be if KEQ is large. KEQ large favors products. So the equilibrium, this reaction favors products to a large extent, okay? So much so that it looks like it goes all the way to completion. What if KEQ is small? Well, here we have a reaction where we have 2NOCl goes to 2NO gas plus Cl gas, chlorine gas. So here we have a reaction that's at equilibrium, and its equilibrium constant is very small, 1.6 times 10 to the negative 5, so extremely small. What does that mean? Again, going to our KEQ expression here, in this case, if KEQ is small, then that means that the denominator is much, much bigger than the numerator, which means, again, the denominator has the reactants, the numerator has the product. So if your denominator is much, much bigger, that means at equilibrium you have a whole lot of reactants compared to products. So in this case, if KQ is very small, then you have very, very, very little product and you have a whole bunch of reactant. So in this case, your reaction favors the reactants. Oops, I'm wrong, pointing to the wrong one. Your reaction favors the reactant. So for this reaction, at equilibrium, you'd have a huge amount of this during the reaction in your reaction vessel, right? So if this is gases, we have this in some sort of reaction vessel. And then we have very little of this, a tiny, tiny amount of this compared to this. So that means that for this reaction, it favors reactants. So much so that when you put them together, it would seem like nothing's happening. It's not reacting at all, right? So, but if you take a microscopic picture or snapshot of what's going on, you would see all three of these in the reaction vessel together. It's just that you would have a very tiny amount of this and a whole lot of this in your reaction vessel. So this would be an example of a reaction equilibrium that favors the reactants very much, right? So it looks like it's hardly reacting, if reacting at all, okay? So that would be if the equilibrium constant is small. What if the equilibrium constant is approximately 1, where the reactants and products are basically equal to each other? What about that? So here we have a reaction that fits that. We have N2O4 gas in equilibrium with NO2 gas, two of them. So basically this is a decomposition reaction where your dinitrogen tetraoxide will break down into nitrogen dioxide, 2 molecules of nitrogen dioxide. And so here we have a reaction that has an equilibrium constant fairly close to 1, where it's not, this equilibrium constant is not really huge, it's not really small either, so it's in that near 1 factor, right? So in this case, at equilibrium, the amount of reactants and products are about equal, right? So again, the ratio is close to 1, meaning the concentration of products and reactants is close to equal, right? Giving approximately 1, right? So in that case, neither the reactants or the products are favored very much. So that's what happens in this case, where you have KAQ equal to 1. So when you look in that, if you take a snapshot of this one, you'll see a whole lot of this and a whole lot of this together at the same time. So the KAQ equals 1, that's going to be probably, if you're like within 100 one way or the other, right? So if your KQ is within plus or minus 100, that's probably going to be enough to indicate that that's pretty much close enough to 1. So again, this example here, KQ is 0.133, so that is definitely close to 1. It's not a very small number, so we would not anything like this here, right? So that's -5, 10 to the -5. That's really, really small. This is small, but it's not very small at all. It's like it's close to 1. So that would be pretty much where the equilibrium concentrations are close to each other at equilibrium. And that, ladies and gentlemen, is understanding the equilibrium constant. I hope this video helped you in some way. If you enjoyed this video, if you learned from this video, then please by all means like the video. share the video, hit that like button somewhere over here. Also, subscribe to my channel, hit that notification bell up there. When you do that, click all, so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me, and have a great day.